Today in section 4.3, we're going to talk about linear operators. Remember, a linear operator is a linear map from a vector space back to itself. So we're only going to be working with one vector space here, or at least in each given problem we'll work with one vector space. But we are going to look at what changes about this linear operator, specifically what changes about its matrix representation if we change the basis on this vector space. So let's take an example. So we'll just look at a linear map from R2 to R2. And we'll just say this is the linear map that takes in a vector xy and returns the vector 5y minus 2x, 3x minus 2y. Now, what is the matrix representation for this linear operator? Well, all we need to do is think about what happens when we plug in our standard basis vectors. So right now we're just working with the standard basis. We plug in 1, 0, and then we plug in 0, 1, and see what we get. And those become the columns of our matrix representation. So here, when we plug in 1, 0, the 5y becomes 0, but we have a negative 2. And then we have a 3 minus 0. So negative 2, 3 is our first column. When we plug in 0, 1, now we have a 5 for this first one. That part's 0. This is 0, and then we have a negative 2. So that is the matrix representation in the standard basis. Now what if we had a different basis? Let's say we have a basis E. And we'll just accept that this will be a basis. Come on, right. There we go. So our basis E is going to be the basis consisting of the vector 1, 1 and 2, 0. And we want to know what is the matrix representation of this same linear map in this basis. Now this is a little bit more complicated to do this directly. We actually have to go ahead and plug these things in and see what we get. It's a little harder to just eyeball it. So I'll go ahead and plug 1, 1 into our linear map. So we'll replace x and y with both 1s. So 5 minus 2 will give us a 3. 3 minus 2 will give us a 1. And if we plug in 2, 0, we have, well, remember that with y is the 0, 1, so this goes away. So we have negative 2 times 2 gives us a negative 4. And then 3 times 2 minus 0 gives us a 6. Now, unfortunately, these are not the columns of our matrix representation. What do we need to actually do? Well, we need to express these two vectors, 3, 1 and negative 4, 6, in the basis E. Right now, they're in the standard basis. So this is 3 times the vector 1, 0, and plus 1 times the vector 0, 1. We need to see what is this vector as a linear combination of the vectors 1, 1 and 2, 0. And when we find those coefficients will become the stuff that we're going to put into our matrix representation. So let's think about how this is built up out of 1, 1 and 2, 0. Well, actually, this one's a lot pretty easy to figure out. So if we just add 1, 1 to 2, 0, we get 3, 1. And that's exactly what we wanted. So our coefficients that we used in that case were 1 and 1. That is our first column, is 1, 1. Negative 4, 6 is a little bit more complicated, but can use the fact that we have a 0 here to make it a little easier. We're going to have that this is equal to 6 times this vector, because this one can't change that second component to 6. So we'll have 6 times that. And then what do we need for the coefficient here? Well, we need to make sure that we have a negative 4, and we end up getting that by putting in a negative 5, because then we'll have 6 times this one here, minus 5 times 2, so 6 minus 10 gives us the negative 4 that we're looking for. So a little bit more complicated, but we are able to do it. Now, how are these two matrices related? They are matrix representations for the same linear map, but they are very different looking matrices. Well, the key comes in our transition matrix. And I wish my pen would write a little bit better than it does. Sometimes it just decides to drop my inputs. So we're going to look at a transition matrix, and just going along with the way the book is doing it for the first examples, we're going to use the letter U. This is going to be a transition matrix specifically from E back to the standard basis, because that's a little easier to find right off the bat. All we really need to do is take the vectors in E and use those for our column. The transition matrix from E to the standard basis is just has first column 1, 1, second column 2, 0. If we want to go the other way, we'd actually have to find what is the inverse of this matrix. So if we're looking for U inverse, well, first of all, we're going to have to find the determinant here. So 1 times 0 minus 2 times 1. 0 minus 2, we're going to have a negative 1/2 out in front, which hopefully won't have any fractions, but we might have fractions. Then we have to take the adjoint of this matrix. What that's going to do is swap the diagonal elements, but then leave the other elements alone and give us a negative in front of them. So we'll have a negative 2 here and a negative 1 here. So even if we brought in the 1/2, we actually couldn't get rid of all the fractions. There are definitely fractions here that we can't get rid of. Okay. So how are these matrices actually related to each other? What is the transition matrix going to do? Well, let's put a diagram. We'll start with R2. And for the moment, we'll just work with the standard basis. And we'll think about what this linear map is doing. It's taking R2 and it's giving us back something in R2. If we're working with the standard basis, all that means is that we're going to multiply by the matrix A. That's what the matrix representation means. So we'll just write down L in this form. You can say this is the map L that goes from here to here, but it is just represented by multiplying by A. We can do the same thing in our E basis. We can go from R2 to E, or R2 on E with basis E, back to R2 with the same basis E. We're still working with the same L, but this time, because we're working in a different basis, it's represented by multiplying by the matrix B. Now, what does the transition matrix do? The transition matrix takes coordinates in E and returns things in the standard basis. So let me make that more vertical. Going from here to here is just represented by multiplying by U, our transition matrix. And we can do the same thing over here because it's really just the same operation. Of course, if we want to go the other way, from the standard basis to E, we'd have to instead multiply by U inverse. This is really you could say a bidirectional arrow, where going one way is multiplying by U, going the other way is multiplying by U inverse. If we want to actually think about how these are related, we can just follow the arrows. think about if we start over here with, in this version of R2, and we want to end up over here. Well, we can go straight there by multiplying by b. So a vector over here, let's just say a vector x, we can get the result over here by multiplying by b. Or we can start here, move it into the standard basis. So instead start with x, multiply it by u, and get a vector in the standard basis. Then we can use L to move it over to here, and using L in this case is just multiplying by a, so u times x is then going to be multiplied by a. And then finally, we want to then put it back into the basis e instead of the standard basis, and this time we need to multiply by u inverse. So we take this AUX, we multiply it by u inverse, and we're going to get the same result. I mean, really all we've actually done here is applied the linear map, or the linear operator L. So we should get the same result. So we have this result where for any vector x in R2, b times x is the same thing as u inverse times a times u times x. Or in other words, we're going to have the result that b is equal to u inverse times a times u. And if you want to go and actually test this out, you can go ahead and multiply these out. If you take the u inverse, this matrix here, multiply it by a, then multiply it by u, or we could do a times u first and then multiply it in front by u inverse. The order doesn't really matter there. But you should get the matrix B. Now it turns out that we can do this same process with any finite dimensional vector space. So here we are going to look at an example, or not necessarily an example, but look at the situation where we have a vector space V, but we have two different bases, E and F. And we're only working with finite dimensional vector spaces here. So both of these have the same length. It's the dimension of V is going to be n, so both of these consist of n different vectors. Then L is going to be a linear operator on V, and we're going to look at what is the transition matrix A with respect to E, and the transition, not the transition matrix, the matrix representation A of L with respect to E, and the matrix representation B of L with respect to F. We're going to use S for the transition matrix for going from the basis F to E. So S is the U that we had in the previous example. I'm not sure why they picked different letters for the first examples versus what they have in this theorem, but that's what they picked. But the idea is exactly the same. If we have our vector space V using the basis E, and we want to look at what happens when we move over to, well, not move over to, but we use L to take us from V back to itself, but using the basis E, so we're still working with L here, where it's just multiplying by A. Now here, we might be working with something that's not in Rn, so we might be working with, say, the coordinates of V in the basis E. And so what do we do there? Well, we go to L of V, still in the basis E, but we get there by just multiplying this coordinate vector by A. So we can just say the coordinates of L of V are A times the coordinates of V in E. We do the exact same thing for F. So here we're going to still be working with the vector space V, but using F instead. And same thing over here. And in this case, we're still working with L, but this time the matrix representation is B. So very similar thing over here. We have the coordinate vector of a little v in the basis F. We still are working with L of V over here, but now still working in the basis F. and we just get there by multiplying by b. But then we have our transition matrix. And remember, this is going from F to E. We're going from here up to here. So the same direction that we had our U in. So still going from the bottom to the top. Of course, this is a transition matrix. Transition matrices are always invertible. We can always go the other way if we need to. So we can do exactly the same thing we did with the U before and go from E to F by multiplying by S inverse. And that's what we get here. We have our S, still have our S, doing the exact same kind of thing, and we still have our S inverse that's involved here. And so we can follow the same path. We're talking about what happens if we start over here with this coordinate vector and we want to end up with this coordinate vector. Well, we can just get there by multiplying by b. That's the direct way of doing it. So b times, well, let me put it this way. Actually, yeah, I'm going to start with b times the coordinate vector of v and f is just the coordinate vector of L of v in f. Wrote that kind of the opposite order what we normally would, but I would want to work with this side first. We are then going to think about, well, what is this? Well, we can get that from L of v and E by multiplying by S inverse. So really, this is the same thing as S inverse times L of v in E. So here we're working with the same vector, but in different bases. Well, how do we get L of v and E? Well, we could just get there by starting with the coordinate vector of v and E and multiplying by A. It's the same thing as S inverse of, or times, A times the coordinate vector of v and E. And then finally, how do we get the coordinate vector of v and E? Well, it's just the coordinate vector of v and f multiplied by s. This is S inverse A S coordinate vector v in f. And so once again, we have this relationship where this b is this S inverse times A times S. That same similar formula that we had before. This time we're using S's instead of U's. But it really just comes down to the fact that we've got this what we call a diagram, a commutative diagram, where if we follow the arrows in one way, we get a different result than if we followed another way. But the results are supposed to be the exact same thing, so we end up with a formula that tells us how these different arrows are related to each other. Well, we're going to use this idea to make a new definition. Now we're going to say that if we have two square matrices, so square matrices are the ones that will represent linear operators, then B is going to be similar to A if there exists a non-singular matrix S such that B equals S inverse AS. Now this is actually a symmetric thing. We don't really need to say that B is similar to A, because if B is similar to A, then A is going to be similar to B. Why is that going to be true? Well, if we start with the statement that B equals S inverse AS, we can then go ahead and move the S's to the other side. That we're working with something non-singular here. So we can turn this into A equals S B S inverse. Now that looks a little bit different from the form that we want, so maybe we'll say that S inverse is some matrix. Let's call it R. Then what is S in this case? S is just going to be R inverse. Basically, the inverse of the inverse is the original matrix. So really what we have here is A equals R inverse B R. We have a different name for the non-singular matrix that works here, but we can get the same form. And it's the form that we're really looking for. So what that's really just saying is that this idea of being similar is something that we can just say, well, A and B are similar matrices. We don't have to give a particular order to it. So we can just say that our theorem 4.3.1 can be stated as just if A and B are matrix representations of the same linear operator, then they are similar. We're not going to be doing too much with the concept of similar matrices right now. I mean, we'll give some examples in the next video, but just keep in mind that this concept of these vectors being, of these matrices being similar will actually play a very important role in what we do in chapter 6 when we start talking about eigenvalues. So there's not a lot of results that we're going to have right now. In fact, most of the results about similar matrices that we'll have in this section will actually be exercises. A couple which will be in your homework, and a few that we'll actually cover in the examples video. So we'll leave that for now, and I'll see you guys in the examples video.